In this video, we will solve this exercise on kinetic friction energy. And it will be an exercise that clearly shows the power of working with the law of conservation of energy. Let's see what we have. We have a solid block that is resting on this inclined plane. The mass of this block is 0.5 kilograms and its middle point is resting at roughly 5 meters above the ground. Now, naturally, because gravity is pulling down on this block, it will start sliding down this inclined plane. When it reaches the ground at this point, it will start sliding over this new surface. And this new surface is a surface which exhibits friction. Its friction coefficient, mu, is equal to 0.2. Now, as you can imagine, once this block slides down the plane and reaches this point of x is equal to 0, it will continue sliding across this plane, but its velocity will decrease due to the friction of the surface. And there is no other force propelling it forward. Thus, at some point, it will come to a halt. And as you probably expect, what we need to find is, given this information, what is the distance that this block will slide over this frictionless surface before it comes to a halt at the position D. So given this information, we need to find a value for D. To solve such exercises, you can easily use conservation of energy without having to deal with calculating velocities and distances and whatnot. What this law says is that energy cannot be destroyed, only transformed into other kinds of energy. Therefore, if we compare the energy of an object at one moment in time, for instance, when it sits at rest at the top of this slope, and at another point in time, when it is again slowed down and has no velocity on this frictionless surface, then the total energy should be the same. The only thing that happens is that energy is transformed from one type to the other. For instance, from potential energy to kinetic energy, or potential energy to kinetic and frictional energy. Therefore, we want to calculate the total energy of the object for these two scenarios. First, atop of this inclined plane, and secondly, when it comes to rest at this distance d. So let's first look at the first scenario. The total energy of this scenario is equal to the kinetic energy plus the potential energy plus the frictional energy. Now this is equal to 1/2 times the mass times the velocity squared for the kinetic energy plus m times g times h for the potential energy, with m being the mass, g the gravitational constant, and h this height above the ground, plus mu times f times d, which is the frictional energy. However, in this scenario, we can already drop two types of energy. The kinetic energy is not relevant here, because at the start, this block is stationary and does not have any velocity. Also, this frictional term can be dropped because we assumed that the inclined plane does not have any friction to the surface, so it will slide on a frictionless plane. It's only in this second part that the surface will have a friction. Therefore, the only energy stored in the system at this point is potential energy, m times g times h. In the second scenario, the block will have slid across this frictionless plane and has come to a halt. Then the energy of this scenario in general is the kinetic energy plus the potential energy plus the frictional energy. And this is again 1/2 times m times the velocity squared plus m times g times h for the potential energy plus mu times f, the normal force, times d, the distance over which the object has slid. Now again here, not all of these types of energy are present. In fact, again, the kinetic energy drops out because we are at rest. And also here the potential energy drops out because we are at 0 elevation above the ground. So we don't have any potential energy. And we see that the only energy left is this frictional term. And in this case, it's the energy that the object has given away to the frictionless surface. It's not present anymore, but it is energy lost, so we need to account for it in the law of conservation of energy. And now comes the beautiful part. because we have conservation of energy, we know that the total energy at the start cannot be lost, so it has to be equal to the total energy at the end. Which means that the potential energy at the start has to be equal to the frictional energy that the object gave away to the surface when it comes to a halt. And this gives us a very nice equation that we can solve. Namely, that we have m times g times h, and this has to be equal to the following. Mu, which is a frictional constant, multiplied by the force which causes the objects to rub against each other, so in this case the normal force, which is the gravitational force, but we'll get there in a second, multiplied by d, which is the distance over which the frictional force was applied. In this case, it started from where the object hit the ground, so x is equal to 0, to exactly d, the distance when the object comes to a halt. So we know that this d is simply equal to the d that we're looking for. And as I said before, this F is the force that caused the object to experience friction. In this case, that would be the gravitational force pulling the object against the ground and thereby causing the friction. And of course, we know the expression for the gravitational force, which is simply m times g, the gravitational constant. And this is the equation that we now have and that we can very easily solve in order to get this distance d. What we can clearly see is that the mass m drops out on both sides of the equality sign. The gravitational constant also drops out on both sides, and what we're left with is simply the following. We get that h, the height above the ground that our object started with, is equal to mu, the frictional constant, multiplied by d. Rewriting this to isolate d, we get that d, the distance that we're looking for, is equal to h divided by mu. And therefore we get that d is equal to 5 meters divided by 0.2, which is equal to 25 meters. And we see that the units also check out, which is always a very important requirement to check. And with this, I thank you for watching, and I will see you in the next one.